and welcome to the last talk at HEXACON. Thanks you all for joining, and I hope you had a fantastic time at this conference. So, my name is Nguyen, also known as the Flow on social media, and today I'm going to talk about BDJB, a Blu-ray disc sandbox escape. And the content of this talk is the following. First, I will give an introduction about myself and the motivation behind this work, and then I will briefly cover the Java security model, and I will present vulnerabilities that I've discovered, which allowed me to escape the sandbox. And next, I will explain how I got native code execution with them, and how I even managed to get arbitrary code execution. And finally, I will talk about the very first public kernel exploit for the PS5, and at the end I will do a quick recap of all the topics. About myself, I'm an information security engineer at Google. I'm doing cloud vulnerability research with focus on low-level security, and I'm also a PlayStation console hacker and have been in the scene for over 10 years. For the PS Vita, I've released multiple jailbreaks, which allow people to run homebrews on their devices. And my latest work, for example, is the GTA San Andreas port, where I managed to load the Android binary on the PS Vita and made the game fully playable. And we even fixed quite a few bugs and added a bunch of improvements. And for the PS4, I've mainly focused on FreeBSD kernel exploitation. For example, the last 3 public jailbreaks are using kernel vulnerabilities found by me. So what was the motivation behind this work? Of course, as a PlayStation hacker, I wanted to hack the PS5, and for that I needed to have an initial entry point. And all public userland exploits so far were based on WebKit, but the PS5's AMD CPU newly supports execute-only memory, which they enable for all the text segments. And this mitigation makes a WebKit exploit much more difficult to pull off, because JIT is not enabled in the renderer process. So in order to get native code execution, we would have to write a ROP chain. However, since we are blind, we cannot read executable pages, and so we cannot identify ROP gadgets. And the other reason is that the WebKit sandbox has improved lately. For example, access to dev files has been restricted, and apparently syscalls like IO control are now blocked. And the main motivation, however, was to explore different attack vectors. I wanted to work on a novel technique, one involving physical access using a USB device or a disk. And for those, exploiting the file system is a possibility, as their implementations are in the kernel. A successful attack would grant you kernel privileges immediately. However, that is quite difficult, especially blindly, because we need to somehow determine addresses, make calculations in order to bypass ASLR. And for that, having scripting capabilities are of desire. It turns out that Blu-ray discs can run Java code, which is a very interesting attack surface. Blu-ray disc Java is supported on the PS3 to PS5, on the Xbox One, Xbox Series X, and other Blu-ray players. And it is used for advanced content, such as games, menus, interactive videos, and more. And there are tools which are publicly available for signing jar files. More details can be found at blueplay.com. People there have written small homebrew games for Blu-ray discs. So what is the attack surface of BDJ? We have 3 vectors. We have JVM, which parses and executes Java bytecode. We have GNI functions, which are native methods, and we have Java classes. For JVM, we can search for OpenJDK CVEs and look out for memory corruption bugs. Unfortunately, there are not many proof of concepts available for these. And for GNI functions, we can also search for memory corruption bugs in their C++ implementations. The BDJ stack contains a lot of custom functions, but that needs a lot of reverse engineering. And for Java classes, we can search for Java privilege escalation bugs. While it is a small attack surface only, it is obvious what to look for. And that is the attack vector that I focused on for 2 months and found multiple vulnerabilities for. And as a setup for this research, I ordered a BD burner and some BDRE disks. Note that BDR disks are only writable once, and since you cannot load classes remotely, you have to burn the disk again and again for every test. Now, let me briefly introduce you to the core concepts of the Java security model. And for that, I will paraphrase a few sentences from the Java documentation. The Java security model is based on controlling the operations that a class can perform when it is loaded into a running environment. For this reason, this model is called code-centric or code-based. A security policy defines the protection domains of an environment, and a protection domain associates permissions with code sources. The TLDR is every class file is associated with certain permissions. Bootstrap classes have full permissions, while untrusted classes, like on our Blu-ray disc, have a few only. The access controller is an important component for the Java Sandbox. It is a class that is used for access control operations and decisions. In particular, there are two main functions. Check permission, which checks that the intersection of all permissions of each protection domain on the call stack implies the requested permission, and do privileged, which is used to run a method in privileged context. And how it works is it marks the caller as privileged in order to ignore all permission checks before the caller. And next, we have the security manager, which is a class that allows applications to implement a security policy. And it also contains a check permission method, which essentially calls the access controller check permission underneath. To show you an example of a security check, consider the following code. Get property of the system class gets a property based on a key. However, before doing so, it checks whether the user has the necessary permission. If a code source without the necessary permission calls this method, then a security exception will be thrown. And if a trusted class wants to call this method, but untrusted functions are on the call stack, then the intersection of all permissions will be empty. And in order to avoid this, the trusted class needs to use doPrivileged in order to ignore earlier functions on the call stack so that the permission check can always pass. Now that we know a bit about the security model, let's see how we can break it. When the Java application is executed from the Blu-ray disc, JVM is launched with the following flag. These are bootstrap classes which are fully trusted and hence have full permissions. For example, the bdjstack.jar contains many interesting classes. And as mentioned earlier, finding privileged escalation bugs in Java is straightforward. You basically search for doPrivileged calls and see if malicious stuff can be done. For example, creating objects or invoking methods in privileged context. The first vulnerability is in the user preference manager, where doPrivileged is called. And in the privileged context, a file is read from hard disk and deserialized using read object. You're probably familiar with Java deserialization bugs. They often allow remote code execution, but they may also allow privileged escalation. Let's see how. The file that gets deserialized is located in a folder in which the user has write access to, and hence the file can be overwritten with a malicious serialized file. What happens during deserialization is that the accessible default constructor is called for the first class in the inheritance hierarchy that does not implement serializable. Since the invocation is in privileged context, permission checks in the constructor can thus be bypassed. And what class would be interesting to instantiate? The class loader is an interesting target. We create a subclass which extends the class loader and implements serializable. And as mentioned before, the first constructor whose class does not implement serializable is called. And since the payload class loader implements serializable, its constructor is not called, but the constructor of the superclass, which is the class loader. And hence, the payload class loader will not be on the call stack, and permission checks in the class loader will pass. When read object is called, we then assign the instance to a public static variable. And once we have the instance, we can call new payload on it. The interesting part is we can now call the protected method define class to load the payload class with an arbitrary protection domain. In our case, one with full permissions. Unfortunately, this has been mitigated upstream in 2017, and exploiting Java deserialization for privileged escalation is no longer possible. The second vulnerability is in the IXC proxy class, which is able to invoke a method by its name and signature on a remote object. The function invoke method does a doPrivileged, where underneath a method is located and invoked with arbitrary arguments. What kind of methods can be located? Methods that can be located are those which are public and non-static, whose classes implement an interface, and where the interfaces methods throw remote exception. On the right-hand side, you can find such an example. We have my interface, which declares my method, and we have my implementation, which implements my method of my interface. How is this useful though? If we just call an untrusted method in the doPrivileged block, we won't be able to gain any privileges. What we need to do is to call a trusted method with it. Consider a target method which is public and non-static, and where the target's methods class is inheritable and instantiatable. For example, consider target method in target class, which is from a trusted code source. We can invoke this method in privileged context as follows. We create an attacker interface which declares the same target method, however, which throws remote exception in addition. And we create an attacker class which extends the target class and implements attacker interface. What is important here is that the attacker class does not override the target method. Namely, target method is inherited from the target class. When locating and invoking this method, the untrusted attacker class will not be on the call stack, meaning that everything within the doPrivileged block will come from trusted code only. For a real example, consider the file class as a target. Permission checks are not in the file constructor, but for example in the list method. We create a file interface which declares list, and we create a file implementation which extends the file class and implements the file interface. With our primitive, we can now call list with all permissions, and therefore we are able to list paths outside of the sandbox and use that to dump the application directory and obtain jar files on the PS5. With the ability to call methods in privileged context, we can invoke a few interesting methods. However, there are certain limitations as described earlier. And with the following gadget, which is only available on the PS4, we can instantiate a class with one argument. Chaining that with the privileged method invocation, we can now also invoke constructors in privileged context. And the last piece of the puzzle, the BDJ stack contains its own security policy implementation, and in the getPermissions method, there's an interesting condition. If the location of the code source begins with a certain prefix, all permissions are granted. And that is the #1 mistake when handling and checking file paths. If path traversal is possible, then we can trick the security policy into giving us all permissions. And plugging it all together with our privileged constructor invocation, we can instantiate a URL class loader with a malicious path. We namely point it to the jar file, but with a prefix that fools the security policy. The path traversal per se is not a vulnerability because creating new class loader instances is not permitted in the first place. And this method only works on the PS4 because the service class is available there only. The sandbox escape for the PS5 is a bit different and has been achieved by other members in the scene. So what shall we do with all the permissions? The payload class has one purpose only, which is to disable the security manager. And that can be achieved by setting it to null. With the security manager disabled, all permission checks will now pass, and we can now also access internal classes. The most interesting class to access is the SunMISC unsafe class, which we can get an instance of using reflection. What this class allows you to do, you will learn next. Namely, once you get access to the unsafe class, you get native code execution. And for that, we want to have 3 primitives that are accessible from Java. We want to access native memory. That includes allocating, freeing, getting and setting native memory. We want to find native methods, which is we want to know the addresses of these native functions. And most importantly, we want to call native functions. We want a way to invoke these functions with arbitrary arguments and also get the return value. Native memory access is for free because that is what the SunMISC unsafe class is for. It contains methods like getLong, putLong, allocate memory, and free memory, which allow you to read, write, and allocate free native memory. We can also construct an address_of primitive to return the native pointer of any object. And we do so by putting the object's pointer into the value field of a long object, and then we can simply retrieve that pointer. As mentioned at the beginning, the PS5's AMD CPUs newly support execute-only memory, which they enable in both kernel and userland. And with this mitigation, we are not able to read executable pages and, for example, identify functions based on opcodes. We can read the data segments, though, which is useful to infer addresses of certain functions, but that is quite cumbersome and only works for a few functions. It turns out that the class loader contains a static class called native library, which contains the native function findEntry that calls dlsim underneath. And that is the perfect primitive, as it allows you to identify addresses of all exported functions from Java. And it is also firmware agnostic, as you only need to provide simple names. The last primitive we need is a way to invoke these methods from Java code. In particular, we want to invoke them with arbitrary arguments, and we also want to get the return value. And for this purpose, there exists the interesting function called setContext, which is a function from libunwind. And it is similar to longjump, but it also restores all argument registers, which is a perfect gadget for function invocation. However, to make this work, we first need to get all other registers like RBP or RSP so that we can restore them safely. And for that, we can use setJump, which works under the assumption that the registers remain the same between the two calls of setJump and setContext. How can we trigger the gadget? We need to achieve rep control. And for that, we need to find an interesting object that we can fake or corrupt, which contains a virtual table that is virtual function pointers, and where the return value of the virtual function is sent back to Java code. We don't need to control any arguments except the first buffer of the buffer of the first argument, which is essentially this object. And the array class contains an interesting virtual function. It is called by the native method multi-new-array. And the array class object comes from the first argument, which is the component type. The interesting property about this function is that its return value is the object that is returned by multi-new-array. In other words, the return value is sent back to Java code as we desire. And we will call this virtual function as follows. We declare a native method in our API class and resolve it to the native function using our dlsim primitive. And we do so because we want to have different types. Instead of returning an object, we return a long. And instead of using a class as the first argument, we also want to use long. And then we can call this, it with a fake object as component type. And this fake object we can simply allocate on the heap. And as function pointer of multi-allocate, we first use setJump to save all the registers. And then we use setContext to restore them and to provide our desired arguments and function pointer. And with that, we have basically achieved robless code execution. There was a problem on the PS4 though. After a lot of function calls, it would just crash. And for some reason, the stack pointer might differ between the two multi-allocate calls. Remember, the first call is to setJump and the second to setContext. It turned out that JIT optimization would kick in between these two calls. And the solution to that was easy. I used a loop for the two multi-allocate calls, and then I trained the Java function by calling it more than 10,000 times with one iteration only. And this trick was enough to trigger JIT optimization at an earlier stage. And that way, the stack pointer would remain the same afterwards. After all the hard work, we have finally achieved a native API with all the desired primitives. We can allocate, free, and access native memory. We can find native functions, and we can also invoke them with arbitrary arguments. The exciting thing is it can even be used in Java threads, which means that we can do native function calls in parallel, which is useful to exploit race condition bugs in the kernel. With native code execution, we can call some native functions, but we cannot yet execute arbitrary code. We can't simply call mmap because JIT capabilities are only granted to certain processes. In particular, no process is allowed to call mmap with write executable permissions. Instead, one needs to set up a shared page, which is mapped as read executable in one process and read writable in another process. And that's what Sony did on the PS4. They moved JIT functionalities of the JVM runtime to a different process and communicate with it with Unix domain sockets. On the PS5, JVM JIT is unfortunately not supported. To show the concept visually, the runtime process maps the JIT page as read executable, and the compiler process maps the JIT page as read writable. Via Unix domain sockets, the runtime process can request the compiler process to do JIT compilation, which is to write to the JIT page, and then to receive the result from the compiler process. If we manage to exploit the compiler process, then we can write arbitrary payloads to the JIT page, which the runtime process can then execute. The third vulnerability is in the protocol between the two processes. Namely, the runtime process can provide an untrusted pointer in the structure, and the compiler process will simply make a backup of the request at that location. In other words, we have a write what where primitive. Exploiting the bug is quite easy. We don't really need to get code execution in the compiler process. We can simply use the write primitive to write our payload. And that works because the JIT pages have the same addresses in both the runtime and the compiler process. So we let the compiler process write our payload, and then we can simply execute it in the runtime process. And that allows us to write C code as the next stage of the exploit chain. As said before, on the PS5, JVM JIT is not supported. Otherwise, this could have been useful already to run homebrews. On the PS4, this capability is quite practical for kernel exploitation because there's no supervisor mode execution prevention, so one can simply return to the C payload from kernel. And there's some bonus material today. Namely, I'm going to talk a little bit about the very first kernel exploit for the PS5. The fourth vulnerability is in the packet options that can be triggered via the set sockopt syscall. What is most important here is that there are no locks in the socket option. And the function fetches a pointer to the packet options and then sets the pointer to null. Then there are several paths where the options are handled differently. If the AMPAth is empty, the packet options will be freed, and otherwise it will reassign the packet options pointer. And the problem of this code is, since there are no locks, two threads can fetch the same packet options pointer, where one of them can free the pointer and the other can continue using it. And that is a pretty straightforward use of the freed scenario. And this bug can be triggered with our more powerful Java code. We can spawn a race thread which continuously tries to use the packet options. And in the main thread, we continuously try to free the packet options. We can even use Java sync primitives to coordinate the race. And if we win this race, we have a dangling pointer, and we can reclaim the freed object by spraying. And this use of the freed object is very powerful. There are lots of socket options which operate on the dangling pointer. We can, for example, leak kernel pointers with the RT header socket option. And we can read and write 20 bytes of almost arbitrary contents to any memory address using packet info. Packet info is a pointer in the packet options structure. And since we can control the whole structure, we can fake the packet info pointer. And I could easily exploit this vulnerability to enable the debug settings on the PS5. And what is funny is that this is a vulnerability I reported to PlayStation in March 2020 for the PS4, which was before the PS5 was released. And 2 years later, I reported it again because for some reason they forgot the patch on the PS5. And that was the whole exploit chain. To recap, to get from Sandbox code execution to kernel memory access, we first need to escalate privileges. We do so by searching for two privilege calls, and we try to trick bootstrap classes into loading our payload class with full permissions. And once we have full permissions, we disable the security manager by setting it to null. And then we can install our native API, which should have 3 primitives. First, we need native memory access, which we can get using the sunmisc unsafe class. Second, we need to find native functions, which we can find using the find entry method. And third, we need to be able to call these functions, and we can do so by using setJump and setContext via the multi-allocate function call. And finally, on the PS4, we can execute arbitrary code by sending malicious requests to the compiler process. And to access kernel memory on the PS5, we can use the IPv6 packet options vulnerability. And the end result is a user-land exploit using a Blu-ray disc. And since it does not rely on race conditions, heap spraying, or other techniques, it is 100% reliable. And it is also firmware agnostic because it only relies on a few structure offsets. And hence, with a single disk, we can hack any firmware. The exploit works on the PS4 below version 9.5 and on the PS5 below version 5.0. The kernel exploit works on the PS4 below version 7.5 and on the PS5 below version 5.0. And the source code of BTJB is available on GitHub. Feel free to check it out and also make pull requests. And with that, I would like to conclude the presentation. Thanks to Sonny for approving this talk, and thank you all for your attention.